Most broadcast and media infrastructure engineers inherit OSPF. It was there when they arrived. Nobody questions it. But the largest ISPs in the world, the organizations running the most demanding high-throughput networks on the planet, don't run OSPF in their cores. They run ISIS. Today, I am going to tell you exactly why. And more importantly, I'm going to explain what that decision means for the media and broadcast networks you are designing right now. ISIS is intermediate system to intermediate system. It is an ISO link state routing protocol. It was originally designed to route OSI CLNMP packets, not IP. That distinction mattered. What you're actually deploying in modern networks is integrated ISIS, the extension that adds IP routing capability while the protocol itself still communicates between routers using OSI PDUs. Like OSPF, ISIS uses the Dijkstra SPF algorithm to compute shortest path trees. It floods link state PDUs, LSPs, not LSAs. The topology database is built the same way. Every router holds a complete picture of the network, and routing decisions are made locally from that picture. Neither protocol is proprietary. Both are open standards, but they diverge sharply in architecture. And that divergence is where the engineering story gets interesting. Let's talk about the architecture difference that changes everything. Here is the single most important architectural distinction between ISIS and OSPF. In OSPF, area boundaries sit on routers, and ABR, an area border router, sits with 1 foot in area 0 and 1 foot in a non-backbone area. It maintains separate link state database for each area. The router is the boundary. In ISIS, area boundaries sit on the links, not the routers. Links. Remember that. This is not a subtle difference. It changes how you design, how you summarize, and how you contain a failure domain. ISIS uses a 2-level hierarchy. Level 1 handles intra-area routing. Level 1 routers know only their area. For anything outside, they follow a default route towards the nearest level 1/level 2 router. Level 2 handles inter-area routing. Level 2 routers form the backbone, a contiguous path of L2 adjacencies across the network. Level 1/2 routers sit at the boundary, maintaining separate link state databases for each level. For media networks, the implication is direct. Your core switching fabric, whether that's an IP MPLS spine, a routed data center fabric, or an interconnected broadcast facility network, maps directly onto a flat level 2 domain. Simple, single database, fast convergence, no ABR complexity. If your infrastructure spans multiple facilities or geographic regions, the hierarchical model gives you summarization and failure isolation. This is critical, especially between sites. Without the ABR state explosion you get in large OSPF deployments. Let's move on to understand a bit more about why ISIS lives in the ISP core and what that means for you. As I said, it is the IGP of choice for the world's largest ISP backbones. The reasons are engineering decisions, not preference. First, protocol transport independence. ISIS doesn't run over IP, it rides directly over layer 2. using OSI PDUs. This means ISIS is immune to IP stack issues that can destabilize OSPF adjacencies. In a high-throughput broadcast routing environment where the control plane must remain stable under load, that matters a lot. Second, simpler TLV extension model. ISIS uses type length value fields in its PDUs, adding new capabilities, traffic engineering extensions, V6, MPLS. It doesn't require a new protocol version. You just add a TLV. OSPF required new opaque LSA types and version extensions for equivalent functionality. The result is that ISIS has historically been faster to adapt to new forwarding paradigms. Third, scalability under load. In a large network with many nodes, LSP flooding frequency directly impacts CPU, memory, and conversion stability. ISIS gives you coarse-grained control over that flooding with two critical timers: LSP refresh interval, which is how often an LSP is re-originated, and max LSP lifetime, which is how long an LSP lives before expiring. Both can be pushed toward their maximums if need be, approximately 18.7 hours, dramatically reducing the volume of periodic background flooding. OSPF's equivalent mechanisms exist but are less direct to tune across a large topology. For broadcast and media infrastructure architects, if you're designing a network where the control plane must be deterministic, particularly in live production or playout environments, this level of timer control isn't just cosmetic, it is operational engineering. ISIS metrics require your explicit attention. By default, in a Cisco world, iOS assigns a metric of 10 to every active interface, regardless of bandwidth. Left unconfigured, ISIS will route by hop count. That is acceptable in any serious media network. This legacy narrow metric has a single link maximum of 64 and a path maximum of 1024. For modern high bandwidth environment, 10 gigs, 25, 100, and so on, that range is insufficient. You cannot represent meaningful differentiation between a 1 gig link and a 100 gig link with a maximum value of 64. The solution is wide metrics. They extend the per link value to 16 million and change, and the path metric to over 4 billion. Wide metric are also hard requirements for ISIS traffic engineering extensions and for route leaking between levels. Configure wide metrics from day one. That's the best approach. If you are migrating from OSPF, extract your OSPF interface costs and you can port those directly into ISIS interface metrics. The OSPF cost model, reference bandwidth divided by the interface bandwidth, gives you a starting point because ISIS does not auto-derive metrics from bandwidth. That translation should be explicit and documented. Remember that ISIS supports only two interface types, point-to-point and broadcast. There's no point-to-multipoint. In some legacy environments, this becomes operationally significant. Today, in hub-spoke or partial mesh design, in MPLS and overlay architectures, this is relevant. If you model an NBMA cloud as a broadcast segment, ISIS will require full mesh connectivity connectivity between all nodes. The moment a single virtual circuit fails, the flooding model breaks. LSPs stop propagating correctly. The link state database becomes unsynchronized. Routing loops are the consequence of this. The correct approach is point-to-point sub-interfaces. One sub-interface per PVC, each carrying its own IS-IS adjacency. This model is more robust. Individual circuit failures are tracked. Each adjacency is independently monitored in the link state database. In highly meshed environments, point-to-point sub-interfaces create a new problem, however: redundant flooding. Every LSP is potentially flooded out of every sub-interface towards every neighbor. In a large mesh, this generates significant LSP volume, SPF computation loads, and bandwidth consumption. The solution is IS mesh groups. The logic works as follows. A router in a mesh group does not reflood an LSP received from another group member back to other members. They already received it at that point. LSPs from outside the groups are flooded to all members. This selectively suppresses redundant flooding without breaking topology propagation. For most environments, selective blocking is operationally simpler to configure, monitor, and troubleshoot than mesh groups. Mesh groups are the right tool in very large, highly redundant NBMA environments where the flooding volume is measurable and documented. Now let's take a look at OSPF versus ISIS. Let's be direct about the comparison, because this debate in the industry is often either academic or tribal sometimes. Both protocols are link state protocols. Both use the Dijkstra's SPF algorithm, and both support VLSM, CIDR, and V6. And neither is proprietary. In terms of basic routing functionality, they are functionally equivalent for the majority of deployments. The differences that matter in practice are area boundary model. ISIS link-based boundaries mean you do not have dual-homed ABR routers carrying two full link state databases. In large hierarchical topologies, this reduces state and simplifies failure domain containment. Transport stability. For transport stability, ISIS runs over layer 2 and OSPF runs over IP. In an environment where the IP layer itself can be disrupted, congestion, misconfiguration, security events, ISIS adjacencies are more resilient. When it comes to metric engineering, OSPF auto-derives cost from bandwidth with a configurable reference. ISIS requires explicit manual metric assignment. This is a disadvantage if your team lacks the discipline to maintain it. It is an advantage if your network demands precise, intentional traffic engineering. When it comes to extension velocity, ISIS TLV extensibility has historically meant faster adoption of new capabilities like traffic engineering and segment routing and V6 multi-topology. All arrived in ISIS with less architectural disruption. And when it comes to operational familiarity, OSPF is more widely understood across the engineering population. If your team's ISIS knowledge is thin, that is an operational risk that the protocol's technical advantages do not automatically offset or address. For broadcast and media infrastructure architects, the decision criteria are: if your network is contained in a single facility or campus design with standard topologies, OSPF is adequate and operationally safer. If you're designing a multi-site, high availability multimedia network and MPLS or traffic engineering or segment routing is involved, ISIS is the more capable and future-proof choice. If you're working with or adjacent to ISP infrastructure, carrier interconnect, cloud layout, or distributed production, ISIS alignment reduces the architectural mismatch at those boundaries. 3 things to take away from this video. ISIS is not OSPF with a different name. The area model, that transport layer, and the extension architecture are fundamentally different. Those differences are why service providers chose it, and they are relevant to your media network design. 2. ISIS requires engineering discipline on metrics. The default assigns equal weight to every interface. If you deploy it without intentional metric design, you will route by hop count. This is not a routing strategy. 3. For multi-site, MPLS capable, or ISP adjacent media infrastructure, ISIS is the technically superior IGP. The operational cost is higher training overhead and more deliberate configuration. The return is a more scalable, stable, and extensible control plane. That's it. Thanks for watching.